tutorial on how to do electron dot structures and how we can use those to make predictions about ionic bonding between a metal and a nonmetal. So hopefully you have read through the first page of information. We're going to do some work with this diagram on the back, and then you should have the ability to predict what happens when a metal and a nonmetal bonds. So let me jump over to this side. So what we should know at this point is that by column in the periodic table, if we work out the electron configuration, each element in a column should have the same number of valence electrons. And the rules on the front say when we do these dot structures, the dots represent a valence electron. So if I'm looking at hydrogen, lithium, sodium, and potassium, their dot structure is quite simple. We just put a single dot, and my recommendation is to always start at the top with your first electron. And so those would be the dot structures for the first column. Moving to the second column, each of these would have 2 valence electrons, and again, the recommendation is to start at the top and then work clockwise. So the second electron will go on the right-hand side of the element. And again, those represent the 2 valence electrons in these elements. So magnesium, likewise, is going to look like that, and calcium like that. We skip the transition metals. We typically don't do dot diagrams for the transition metals because their electron behavior is so irregular. They don't behave in the same way as our S block and P block elements. So I've zoomed in on the P block over here. We would know if we worked out the configuration that boron and aluminum have 3 valence electrons. So we're going to represent those like this. Start at the top and move clockwise. Aluminum the same. Moving on to carbon and silicon, 4 valence electrons. And then moving on to nitrogen's group, here we have 5 valence electrons. So this is the point where we start to pair up electrons in the electron structure. This pairing of electrons will become, I guess, more important as we move on to covalent bonding, which is sharing of electrons. But this model is very helpful in predicting how elements join together in compounds. So for nitrogen, we're going to fill in the 5 electrons like this. We're going to still start at the top and go 1, 2, 3, 4, and then we show the 5th valence electron as a pair up top. So nitrogen's dot structure will look like that. Phosphorus will be the same. 1, 2, 3, 4, and 5 valence electrons. Oxygen, moving on, we'll have 6. So we're going to go 1, 2, 3, 4, pair up the 5th, and pair up the 6th. Same with sulfur. 1, 2, 3, 4, 5, and 6. Fluorine and chlorine are going to have 7 valence electrons, so again, start at the top. 1, 2, 3, 4, 5, 6, and 7 valence electrons. Just note that kind of doesn't look like it, but that's a single electron in the structure. Chlorine, 1. Try that again. 1, 1, 2, 3, 4, 5, 6, 7. So chlorine structure has a pair here, 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 and a single electron here. Now on to the noble gases. We know again helium is kind of an exception. We'll come back to that in a moment. Neon and argon are going to have 8 valence electrons. So 1, 1, 2, 3, 4, 5, 6, 7, 8. So neon has 4 pairs of electrons. Argon likewise, 1, 2, 3, 4, 5, 6, 7, 8. Now helium, we know actually that it has an electron configuration of 1s2. It only has 2 electrons, and it behaves differently than this column. This column are metals, they're very reactive, they want to lose electrons. Helium is very stable, it does not need to gain or lose electrons to become stable. So we do show its electron configuration a little bit differently than these. What we'll do is actually show a pair on the top. And that helps us realize that helium is going to be different in its behavior than these elements. These 2 electrons that we're showing here are very much unreactive. They don't need to do anything to bond. Helium is already, as a noble gas, very inert and stable as is. So how does this all work to help us predict or show what happens with ionic bonding? Let's take an example that we've looked at before. Sodium reacting with chlorine, sodium metal, chlorine non-metal. And we know that because it is ionic bonding that electron transfer should occur. So the way that we represent that is we start with the dot structure. So we can write sodium with a dot. I'll change colors for chlorine. Chlorine, 7 valence electrons again. So 1, 2, 3, 4, 5, 6, 7. To represent the transfer of electrons, we know that sodium would like to lose a valence electron. In doing so, it drops to neon's electron configuration, which we know is stable. So the electron here is going to be transferred, and we can show that with an arrow. So what I'm trying to show is this valence electron from sodium ends up being transferred over here to the chlorine atom. And so it has been removed from that location. It ends up here. If we think about it, now chlorine has a full octet, it is stable. Sodium has lost that valence electron. It really has dropped down to a previous energy level, but it would be stable as well. And so this tells us that when sodium and chlorine react, we actually predict a 1-to-1 ratio. So the formula for this compound is just NaCl. The 1 here and here is implied. We don't actually include it in the chemical equation. So let's look at lithium and oxygen. A little bit different. Lithium is in the first column, so it's going to react in a similar way to sodium. Oxygen has 6 valence electrons, so let's see how that works out. We'll start by doing lithium's dot diagram. Lithium with a dot. Make that more like a dot. Oxygen, switch colors. Oxygen is in the 6th column, so it has 6 valence electrons. 1, 2, 3, 4, 5, and 6. So if we think about how the electron transfer will happen, lithium has just this lone valence electron that it would like to transfer away so that it can drop down in its configuration to be equivalent to helium. So lithium would love to get rid of this electron and send it over to oxygen. So I'll go ahead and represent that. It has moved. It is no longer here. It has been transferred to oxygen. That lithium atom would be following the duet rule now. It would have a configuration exactly equal to helium, which is very stable. However, the oxygen atom has not yet gained a full octet. It needs to pick up another electron. So that means in the formula unit here, in kind of the smallest unit that the bonding occurs, we actually need a second lithium atom. So there's our lithium represented with its valence electron. And what we're going to see again is transfer of that electron. But now it's going to kind of go in this other location. It gets transferred in here. And it is gone. Whoops. It is gone. From that lithium atom. So what happens in the bonding between lithium and oxygen is you actually need two lithium atoms to react with an oxygen atom. So the formula is Li2O. O implied a 1. We don't write it in the formula, but we need to have these two atoms involved because they each can only provide one valence electron and the oxygen atom needs to pick up two. So NaCl and Li2O. Another thing I might note is when this happens, we do get a charge being carried on these ions. So this sodium atom, once it lost its valence electron, is now carrying a plus charge. It's ionized. This chlorine, because it has picked up a single electron, is now carrying a minus charge. And again, the reason why ionic compounds stick together is positive charges are attracted to negative charges. So this sodium ion and the chloride ion will be very tightly bound together. And just to show that over here, this lithium atom has picked up a +1 charge. This lithium atom has picked up a +1 charge. And this oxygen atom has picked up a -2 charge. And again, the reason why those ions would stick together is they have opposite charge at this point. Moving on to our last two examples. Beryllium, 2 valence electrons. Chlorine, 7 valence electrons. So let's take a look at what its bonding will look like. Beryllium, 2 valence electrons. Chlorine, 7, 1, 2, 3, 4, 5, 6, 7. Make that one a little bit better. And if we look at our transfer here, this beryllium atom would like to get rid of 2 electrons in this case. However, the chlorine atom, it can only pick up a single electron. It has its full octet, so it's not going to accept another electron because then it wouldn't have a noble gas configuration. So what we need here is another chlorine atom, starting off with its regular 7 valence electrons. It would like to accept an electron. So the other valence electron from the beryllium will end up here. And now beryllium has dropped down to the electron configuration of helium, following the duet rule. It's stable. And the chlorine has picked up the valence configuration of argon. So in writing the formula for this compound, sorry about that, we would write BE, there's only one, it's implied, Cl2. And again, if we want to think about the charges on each individual atom, this beryllium atom has lost 2 electrons. So it would now be carrying a +2 charge. Each chlorine is carrying a -1 charge. I'll let you try magnesium and oxygen for yourself. You should find out actually that a 1-to-1 ratio works out. what we're going to see is a formula of MgO. And the reason for that is when magnesium, when you work out its diagram, it would like to lose 2 electrons. It will become charged as Mg2+. The oxygen can accept 2 electrons. It ends up being 2-, and a 1-to-1 ratio is what's needed to make that particular formula.